We want to find a plane that contains a line given by the vector function r of t and is orthogonal to the plane 6x minus y minus 7z equals 0. To find the equation of a plane, we need two things. We need a point in the plane, and we need a normal vector to the plane. Where if the point has these coordinates here, the normal vector has components a, b, c, the equation of the plane is given by this equation here. Let's first write our line, given as a vector-valued function, as parametric equations. We'll notice x of t would be equal to -4 plus 6t. Y of t is equal to 2 plus -4t, or 2 minus 4t. And z of t is equal to 7 plus 2t. In this form, it should be easier to recognize that one point in this line would be the point -4, 2, 7, and the directional vector for the line would have components 6, -4, 2. Also notice how, looking at the equation of this plane here, a normal vector to the given plane would have components 6, -1, 7. Before we find the equation of our new plane, let's look at this graphically. So the given plane is this blue plane here. The red vector is a normal vector to the given plane. The given line is this purple line, and notice how this purple vector is the directional vector for the line. So the equation of the plane we're looking for contains the purple line and is orthogonal or perpendicular to this plane here. Remember, to find the equation of our plane, we need a point in the plane and also a normal vector to the plane. We can pick any point on this line to be a point in our plane, but it is going to take some work to find a normal vector to our new plane. If we find the cross product of the normal vector to the given plane and the directional vector to the given line, remember that vector will be orthogonal to both of these vectors, and that would be this yellow vector here. So notice how this yellow vector is actually in the given plane, which means the yellow vector would also be normal or perpendicular to the plane we're trying to find the equation of. So we can use the cross product of the directional vector of the given line and the normal vector to the given plane in order to find the normal vector to the plane we're trying to find the equation of. And the plane we're looking for is this yellow plane here. Notice how it's normal to the yellow vector, which is the cross product, and it also contains the purple line. So going back to our work, let's go ahead and list the point that we're going to use to find the equation of our plane. Again, any point on this line will work. Let's just use the point when t is equal to 0, which would be the point -4, 2, 7. And the directional vector for this line, we'll call it v sub 1, would have components 6, -4, 2. And the normal vector to the given plane, which we'll call vector v sub 2, would have components 6, -1, 7. So the normal vector to the plane we're trying to find the equation of, we'll call it vector n, would be equal to the cross product of vector v sub 1 and vector v sub 2. Let's go ahead and find this cross product on the next slide. We'll set this up as a 3 by 3 determinant, where the first row would be the unit vectors I, j, and k. The second row would be the components of vector v sub 1, so 6, -4, 2. The third row will be the components of vector v sub 2, 6, -1, -7. Let's go ahead and evaluate this using the expansion by minors method. For the elements of the first determinant, we eliminate the row and column of the I vector, so we eliminate row 1, column 1. So the elements are -4, 2, -1, -7. For the next determinant, we eliminate the row and column of the j vector, so we eliminate row 1, column 2. So we have 6, 2, 6, -7. And for our last determinant, we eliminate the row and column of the k vector, so row 1, column 3. So we have 6, -4, 6, negative 1. And now to evaluate these determinants, in each case we'll find this product and then subtract this product. And let's write this in component form. So the x component is going to be negative 4 times negative 7, which is 28, minus negative 2, it becomes 28 plus 2, or 30, comma. The y component is going to be negative 42 minus 12, that's negative 54, but because we have a minus here, it becomes positive 54, comma. The z component is going to be negative 6 minus negative 24, which is positive 18. So this vector is normal to the plane we're trying to find the equation of, and of course so is any scalar multiple, so we could multiply through by 1/6, but let's go ahead and leave it in this form for right now. So a normal vector to our new plane would have components 30, comma, 54, comma, 18. This is all we need in order to find the equation of the plane, where a equals 30, b equals 54, and c equals 18, x sub 1 equals negative 4, y sub 1 equals 2, and z sub 1 equals 7. So we'd have a, which is 30, times the quantity x minus negative 4, which becomes x plus 4, and then plus 54 times y minus 2, plus 18 times the quantity z minus 7 equals 0. Let's go ahead and distribute. So we have 30x plus 120 plus 54y minus 108 plus 18z minus 126 equals 0. Combining like terms, we'd have 30x plus 54y plus 18z minus 114 equals 0. A lot of times we'll see the constant term on the right side. Let's also write this as 30x plus 54y plus 18z equals 114. But we can also simplify this. The greatest common factor of all these terms is 6. So let's divide both sides of the equation by 6. 30x divided by 6 is 5x. 54y divided by 6 is 9y. 18z divided by 6 is 3z. And 114 divided by 6 equals 19. So any of these equations give us a plane that contains the given line and is orthogonal to the given plane. Going back to our graph would be this yellow plane here. Notice how it contains the purple line, and we can see it's orthogonal to the given plane in green. I hope you found this helpful.